All right, welcome. Today we're going to tackle a real classic, Problem 1.54 from I.E. Irodov's Problems in General Physics. Now, if you know this book, you know it's full of absolute gems. And this one is a fantastic look into what seems like simple motion, a rolling cylinder, but has some really cool complexity hidden inside. Let's get right into it.
So first, let's just get a picture in our heads. If you were to put a little speck of paint on the rim of a rolling wheel, what path does it actually trace out? You might think it's a circle, but it's not. It's this beautiful curve called a cycloid. And the really interesting thing is, the shape and the sharpness of that curve are changing constantly at every single point.
And that brings us to our mission for today. The problem wants us to find something called the radius of curvature. Now, don't let the term intimidate you. All it really means is, how sharply is the path bending at a specific moment? We need to figure this out for two spots. Point A, right at the very top of the cylinder, and point B, on the side exactly level with the center.
So here's our game plan. First, we have to really understand what rolling even means in physics terms. Then we'll zoom in on point A and then point B. After that, I'll show you the one key formula that connects everything together, and finally, we'll plug in our numbers and get the final answer. Sound good? Let's go.
You know, the secret to solving so many of these tricky motion problems is something called the superposition principle. It sounds fancy, but the idea is actually super simple. Instead of looking at one complicated motion, we're going to break rolling down into two way simpler motions that are just happening at the same time. One is a pure slide, and the other is a pure spin. Okay, part one, pure translation. Just imagine this cylinder isn't rolling at all. It's just sliding along, like a hockey puck on ice. In this case, it's really easy, right? Every single point on that cylinder, the top, the bottom, the middle, anywhere, is moving forward with the exact same velocity. We'll just call that v. Now for the second piece of the puzzle. Imagine the cylinder is just spinning in place, maybe on a fixed axle, so its center isn't going anywhere. Every point on the edge now has a tangential speed, which also happens to be v. But, and this is key, look at the directions. The top point is moving forward, but the bottom point is moving backward, and our point B on the side, it's moving straight down.
Now we just add them up, we take the sliding motion and the spinning motion and combine them as vectors. And look what happens. At the very bottom, the forward sliding v and the backward spinning minus v perfectly cancel each other out. The velocity there is 0. And that, my friends, is the definition of rolling without slipping. It means the point touching the ground is, for just an instant, completely still.
Awesome. Now that we've got the basic principle down, let's use it. It's time to zero in on our first target, point A, right at the tippy top of the cylinder. So at point A, think about our two motions. The sliding motion is carrying it forward with velocity v, and the spinning motion is also carrying it forward with velocity v. Since they're in the same direction, we just add them up. And what you get is that the top of the wheel is actually moving twice as fast as the center of the wheel.
Pretty cool, huh?
Okay, what about acceleration? Well, the problem implies we're rolling at a steady speed, so the center's velocity v is constant. That means there's no acceleration from the sliding part of the motion. The only acceleration that point A feels is from it constantly changing direction as it spins around the center. And that's our old friend centripetal acceleration, which always points right towards the center of the circle, so in this case, straight down.
And the size of that acceleration? It's just the standard formula, v squared over r. Since the tangential speed of the rotation is v and the radius is r, that's it. That's our acceleration for point A, pointing straight down. Okay, one down, one to go. We've totally figured out point A. Now let's just rinse and repeat for point B, the one on the side.
At point B, adding the vectors gets a little more fun. The sliding motion gives it a horizontal velocity v. The spinning motion gives it a vertical velocity v, pointing down. So we have two vectors at a right angle. A little bit of Pythagoras tells us the final speed is v times the square root of 2, and it's pointing down and to the right at a perfect 45-degree angle.
And the acceleration? Well, it's actually just as simple as it was for point A. Again, it's purely centripetal. The magnitude is still v squared over r, but this time it's pointing horizontally, from point B straight back towards the center of the cylinder.
Fantastic. So let's take a quick inventory. We've got the velocities and the accelerations for both point A and point B. But the problem didn't ask for that, did it? It asked for the radius of curvature. So how on earth do we get from velocity and acceleration to the actual shape of the path? Well, this right here, this is the magic formula. This is the bridge that connects the two. It defines the radius of curvature, which we write as a capital R. But you have to be really careful here. Notice the little n on the acceleration? That stands for normal. This formula doesn't use the total acceleration, it only uses the part of the acceleration that is perfectly perpendicular to the object's velocity at that exact instant. That's the key.
So what is this radius of curvature, really? Here's a great way to think about it. Imagine you have a whole collection of circles of different sizes. At any point on your curve, the radius of curvature is just the radius of the one circle that would fit perfectly, that would hug the curve most snugly right at that spot. So a really tight turn means a small radius, and a really gentle, flat curve means a huge radius.
All right, it's the home stretch. We've done all the hard conceptual work. We have all the pieces of the puzzle laid out. All that's left is to rearrange our key formula to solve for r, and then plug in all the values we worked so hard to find for points A and B.
For point A, this is actually pretty straightforward. Remember, its velocity was perfectly horizontal, and its acceleration was perfectly vertical. Well, that means they're already perpendicular to each other, so the normal acceleration is the total acceleration. We just plug everything into our formula, r equals the velocity squared, so 2v squared, divided by the normal acceleration, which is v squared over r. The v squared terms cancel out, a little algebra happens, and boom, you get a surprisingly clean answer, 4r.
Now for point B. This one needs one little extra step. Its velocity is off at that 45-degree angle, but its acceleration is pointed straight horizontally, so they aren't perpendicular. We need to find the component of that acceleration that is perpendicular to the velocity. And a little bit of trig tells us we just need to multiply by the sine of 45 degrees. Once we have that normal component, we're back in business. We plug our velocity and our new normal acceleration into the formula, do the math, and we get 2 times the square root of 2 times r.
And there we have it, our final results. At the top, the radius of curvature is a nice, clean 4r. At the side, it's 2 root 2 times r, which is about 2.83r. So, if we compare them, it's obvious that the radius of curvature is a lot bigger at the top than it is at the side.
So what does that actually mean? Well, remember, a bigger radius means a flatter curve. So this tells us that at its very peak, the path of that point on the wheel is tracing a very wide, gentle arc. But as it comes around to the side, the path gets much tighter and sharper. The cycloid is flattest at the top and sharpest near the bottom.
You know, the goal here wasn't just to get the numbers 4r and 2 root 2r. It was about the method. And the big ideas to take away are these. First, superposition is your best friend. Break hard problems into easy pieces. Second, vectors are everything. Direction matters just as much as speed. And third, this idea of normal acceleration is the beautiful link that connects the physics of motion with the pure geometry of a path. It's a powerful set of tools you can use everywhere.
So I'll just leave you with one final thought to chew on. We did the top and the side, but what about the very bottom point, the instant it touches the ground? We already know its velocity is 0. So what happens when you put v equals 0 into our formula for the radius of curvature? The answer is pretty fascinating and tells you something really weird and cool about that sharp little point at the bottom of the cycloid. Think about it. Thanks for diving into this with me.